Good morning, everybody. I'm quite amazed that so many of you are already here, because I'm not even sure I would be here if it wasn't my talk. So thanks for that. Let's get started. I'm Philipp. I generally do a lot about databases, and we'll just dive into that. I'm from Vienna. I always describe it like that. It's the city of fatty food, classical architecture, and good music. But only thanks to Conchita we could win anything. Otherwise, it would be pretty hopeless. Yeah, I work for Elastic, the company behind Elasticsearch, Logstash, Kibana, Beats. Maybe you're using the Elk stack for logging already. I'm part of our infrastructure team, so I'm doing stuff like internal tooling, Docker, AWS, and that in the middle is a Unix pipe. I kind of piped it out into developer advocacy. So I'm spending a lot of time talking about all the good stuff that we do. And in Vienna, I organize 2 meetups, pretty much on a monthly basis. One about databases, and the other one is more on the theoretical side. We read one academic paper each month and then discuss it. And this talk is kind of the combination of the two. So we will start off with a bit of theory. We'll mention a few papers, and then we will jump into a few actual database systems and see how that goes. So without further ado, let's jump into databases. Or actually, how did we get to the point of databases where we are today? It all kind of started in 1970 with a relational model of data for large shared data banks by Cod. That was kind of the starting point. Before that, there were databases, but everybody was doing kind of their own thing. And Cod had this idea we should have a generic model. Everybody can use that model, and everybody builds on top of that, and it's not super application specific anymore. So before that, you use the data store, and you really needed to know how does the storage model work? How is the data actually read and written back? And Cod was this is kind of too low level, and I don't really care that much about it. I just want to have this generic model of how to interact with data. And what he actually got was a relational model and normal form, and that basically led to data independence. So you have a generic model, and then every system that uses that will write that out in some specific way, but you don't really care about those details anymore. So what he defined is not the SQL at the back down here, but he only defined kind of the mathematical part. So you have a free variable t with the attribute name, and there exists a tuple with the attribute's name and dotted age, and that is in the sum of all people, and you have the attribute dotted age is empty, and those two names match. And basically all he did was this relational algebra in the middle. That is what he did. SQL came later. I guess everybody can read that, so basically we're querying for everybody who is alive. And this is kind of nice to interact with. Probably you would not want to do that. But this is what Cod basically did. He just defined the mathematical background behind that, and all the relational databases which we've created since then are kind of based on that generic idea. And then IBM came along and created SQL, even though they called it SQL in the beginning, Structured English Query Language. I think there was a trademark dispute, and somebody else had registered SQL already, and then they just removed a few letters, and that's how we got to SQL, actually. And there's another very nice paper by the IBM people, where they tell, yeah, we developed all of that, and it was all very nice, and then this guy came along and asked us for lots of internal details. And we just gave everything to him because we assumed, well, at IBM you can tell everybody anything, because nothing gets done anyway. Which is probably still true for IBM. And that guy was actually Larry Ellison, and he built Oracle very strongly on the foundation that IBM started, and he's the only one who got really, really rich because of that. So that's kind of like a bit of the history of how people got rich around the SQL ecosystem. And one of the very nice things about that is that it's declarative. So you don't really care how the database implements anything deep down on the storage level. You just tell it what you want, and it actually figures out, or the query optimizer figures out what you really need and how to actually get to the data. And you don't need to care about how do you loop over your entries of data and how do you do anything in particular. You just declare, this is what I want, but I don't really care how you do it. That's up to you. And you can already tell it's a bit like for user interaction, so you have some things that users probably don't want to care about, because in the beginning, SQL was kind of like a revelation. Like, even untrained people, like, whatever people wanted to query data, suddenly you didn't need to have the proper programming knowledge to actually query data, but you could write just 1 or 2 lines of SQL code, and you could extract a lot of meaningful information already. But these users are probably not the right ones for aggregations and know how concurrency works and things like that. So all of these features were then taken over by SQL, and you don't really need to take care of them, because that is what SQL already provides. In the beginning, it was very much for user interaction built as well, which is kind of hard to understand or imagine nowadays, because most of us are just interacting through a program with SQL. But in the beginning, it was kind of a very easy way to interact with your program. And then Cod did something else that was very nice. He defined Cod's 12 rules, because even back in the 70s and early 80s, people were very much into buzzwords. And relational databases were a buzzword back then. And all the database providers who were doing something that was not a relational database, they just tried to add 1 or 2 little features from the relational model, and then said, oh, we have a relational database now. And Cod was like, no. Here are these 12 rules, and you need to adhere to all of these 12 rules. And actually, there are 13, because like every good person in IT, he started numbering at 0 and went down to 12. He defined what you actually need to do to be considered a relational database. And that helped tremendously that all of the relational databases we have today, like there are minor differences in the SQL syntax, but in general, the model is everywhere the same. So if you know one system, you can very easily switch to another one because it's very similar. And that's partly because Cod really defined like what you need to do to be a relational database. And thanks to that, they're all very similar. Whereas we will see the NoSQL world is more like the Wild West. Everybody is just building whatever they feel like. And yeah, buzzwords. Everybody wanted to do relational databases, even if we were not qualified for that. Even Dilbert's boss wants to build a relational database, and you can clearly tell he doesn't know what he's doing. And in the beginning, you had kind of this explosion of relational databases, and there were so many systems, and there was a lot of involvement, and everybody built something. And then people kind of fell into a dark age of databases. And I always describe it like this. This is pretty much a dark age. So you had lots and lots of small vendors in the beginning, and then a few big ones took over and either made the other ones redundant and threw them out of business, or just bought whatever was left. And then you were pretty much stuck on these choices. And there's a very nice blog post comparing it to beer, actually American beer, and they say like, this is pretty much like beer brewing in the US. Like, you had the prohibition, and it was forbidden to brew beer, and people kind of forgot how to produce proper beer in the US. That's how you ended up with the beer you had in the US for a long time. And it took quite a lot of time until all these microbreweries started up and people started to produce decent beer again. And he says, like, pretty much the same thing happened in the database space. While it was not forbidden to build new databases, very few people did it. So people kind of forgot how to actually build a new database. And yeah, you had to relearn it, and now we have relearned it, and lots of databases are being developed. But what was actually the motivation for building these databases? I would say there are 2 trends in general why people were not satisfied with relational databases. The first one is kind of speed. So assume your application is a dog, and you can see the dog would be much faster on its own. And that is the relational database. So the turtle is kind of holding back your fast application, and you can easily scale up your application, but the turtle is really holding you back, or the relational database. So people were complaining about that, and part of that problem is, I think that's the final paper we have, Consistent, available, and partition-tolerant web services, but it's not only about web services, it's about any distributed system. The CAP theorem, which basically states you have these 3 attributes, and you want to have probably all of them. So you want to have consistency. Consistency basically means at one point in time, all the nodes you have in your query, you want to have one answer for one query. So they have a consistent view at one point in time. Availability, all the nodes that you can reach over the network should answer your queries. And partition tolerance, you have a distributed system, and even if the network breaks in between a few nodes, those nodes should still be able to answer your queries. And the paper pretty much describes, like, yes, you want to have all of these 3 attributes, but as you can see, you can have not all 3 of them. Like, there is this little white space in the middle, like, you cannot really go there. You can have like 2 of them. You can have availability and partition tolerance, for example, or any other combination of 2 you can have, but you cannot have all 3 of them. And if you build a bad system, like you could just have 1 attribute or 0. Like it's not a given that you will even have done 1 attribute correctly. And their proof is kind of very simplistic. Like let's assume you have a distributed system and you have 3 nodes and the network breaks in between them. And you have on one side you have 2 nodes, and on the other side you have 1 node. And assume you have a network partition, like the network is broken between them, so you have 2 here and 1 here. Then your system basically needs to decide, if I write data to these 2 nodes here, how does this other side react? The node is up, do I respond to queries? Then I'm potentially not consistent, since I cannot see what has been written to these other 2 nodes. Or am I not available? Then I have consistency, but then I'm kind of foregoing my availability attribute because like I have this 1 node here which is up, but it's just not responding to queries because it assumes like, well, I don't have a consistent state, so I cannot really tell you what is going on. And if you want to tell or explain that to your kids, to your parents, whoever, you can do it with Robinson Crusoe. So Robinson Crusoe, I think he was English, and he was trying to buy slaves somewhere, but he got stranded on his lone island. And what kind of happened is, like, Robinson Crusoe was partitioned from the rest of the world, and then the assumption is some ship will come by and asks him a current question, like, who is the king of England? And then Robinson Crusoe can decide, am I consistent or am I available? So if he is consistent, he's not saying anything because he's not sure who is the king right now. Or he is available and he just says the last thing he knows, but then he's potentially not consistent with the rest of the world. And that is pretty much the decision you need to make in any distributed system. And you will need to make that decision kind of explicitly, otherwise random stuff will happen if you have any failures. And then there is this thing called eventual consistency, where after some point in time, your data will catch up to a previous state. That would be like if he gets a message in a bottle every now and then with a newspaper, and he sees like, who is the king of England? Like, who was the king of England like a month ago? And in today's distributed system with computers, the latency is probably more like seconds than months, but there might be this delay of eventual consistency. And then the first thing lots of people are arguing is like, oh, my network is so stable. And this guy, Kyle Kingsbury, he's kind of destroying databases on a professional level, and he made a very nice collection of all the stuff that can go wrong, and he collected, like, in the data centers of Microsoft, Amazon, Google, how many switches are breaking on average, how many racks are getting lost, how often is an entire data center not available. And he kind of shows like how easily the network breaks and that there is no real way around it. And if you think your network is super stable, probably you're just not monitoring it well enough. Yeah. And then there's also another very nice website which actually says everybody who says like they beat the CAP theorem, they have probably no idea of what they're doing. And he has kind of a checklist, and it's like, I don't know, 40 points or something like that, all the reasons why you probably have not bet the CAP theorem. And my favorite is this one. My favorite is the one where he says, like, you just should not be in charge of people's data because you have obviously no idea what you're doing. Okay, so the kind of the slowness and the distribution model, that was one of the pillars of why people were not satisfied with relational databases anymore. The other one is schema flexibility. So in schema flexibility, you could have there's kind of the thing that is not useful for data stores. You just have bytes on disk. There is no structure at all. You cannot really extract any meaningful information. So that is not helpful, but that is basically a blob. Like if you have a video and there are no annotations, it's just like data. No meaningful way to query that. The next thing, the least structure you could have is just key value. You can query over the key, and you can extract the values from that. If you just know what is in the value, you cannot search for that. Like just knowing what is in the value, you have no way of searching for that, unfortunately. Then you have this bag of, I don't know, medium data structures. Like you could have graphs, for example, like you have nodes and edges between them. And this is very good if you want to find the shortest path between two people. So if you're kind of on a job network and you know like who is connected to who over how many people and who these people are, this is what a graph is great at. So it can traverse very easily over these edges. Then you have documents. Yeah, we tried with XML in the past. Nobody likes XML. Now everything is JSON. So yeah, but JSON documents, that is kind of the generic document store. And then you have the column-oriented families, which looks a bit two-dimensional, but you actually have a third dimension as well. You can see you have a timestamp in these as well. So you don't just have a family group, and then you have values in those, but those values then are time-stamped. And at different points in time, you could have different values. So instead of kind of the tabular view is pretty two-dimensional, that one would be rather three-dimensional. So those are kind of like different data structures with a bit more structure than a key value store. And that is what the good old relational databases give you. So you have a very strict schema, and you can see you have joins. Like normally in the other structures, you don't really have joins in that regard. And all of that in combination led to NoSQL, which is not NoSQL, but not only SQL, basically. Even though that is potentially one of the worst names you can have, because not having SQL was kind of not the starting point. So the history of the term NoSQL was some Italian guy started a project that was kind of using a relational structure behind the scenes, but he left out an SQL interface, and you just had to query the data in a different fashion, and that was called NoSQL. And he put that up on SourceForge, I think, and both his project is dead, and SourceForge is probably dead as well. And the project was gone at some point, and then these other non-relational databases appeared, like MongoDB came along, Cassandra came along, HBase, and I think 10 years ago or so, they wanted to do a conference together in San Francisco and just discuss like all the stuff that you can do if you kind of go beyond this relational model, and they were looking for a hashtag, and kind of NoSQL popped up as a hashtag, and it has been sticking around since then. But probably no-rel for no relationship would be the better name, because like generally they don't really have relationships and joins, whereas you can bolt on an SQL interface on top of most of the NoSQL systems, as we'll see later. And some people say this is actually how you get the name of NoSQL. Like everybody knows the recruiter who will tune your CV just to be able to sell you better to your clients. And that is like, if you don't know SQL, well, you just know SQL now to improve your CV. And it always or often goes hand in hand, like you have this term of big data. And yeah, Dilbert's boss really believes in big data because it will make him rich. And yeah. Big data is kind of one of these really overloaded terms, which to me doesn't mean much. So my assumption is always, you have these two definitions basically. One is very broad, like everything that doesn't fit on your laptop is big data, or which you cannot manage in Excel anymore. And the other one is a bit smaller, which is kind of like it's just data warehousing, and you have something, you throw Hadoop and Spark at it, and probably that is big data. But still then, I think it's a very generic term, and it's very buzzwordy, and people are throwing it around. So I'm all for that. Just let's just get rid of big data and not use that anywhere anymore. It's really not helpful. Okay, so let's see some actual systems. So there is this site, dbengines.com, and they do a ranking of databases. They're pretty much like the TIOBE index for programming languages, and they just have this ranking how popular or widely used databases are. And I've used them for a long time, and a few months ago I figured out that the people behind that site are actually based in Vienna as well, and I even did a meetup with them now, and they explained kind of how they evaluate the different systems. And it's kind of a pretty elaborate system where they have like, I think they have 12 or 13 different sources, like they do Stack Overflow, and they get data from search engines and from job boards. And all of that is kind of combined and then normalized, and they have like different categories. And then they try to kind of find the most widely or important databases. So their current ranking looks something like that. You can see the relational databases are still on top, but you can see they're also losing quite a lot of these points, however they're calculated. And you can see the NoSQL databases are kind of pushing in there, but they are not always growing. So MongoDB has been in place 4 for quite some time, but by now Postgres has overtaken it again, and these two are pretty much fighting for spot 4 and 5. What I always find super amazing is that Access is in there, and I'm not even sure like Access should be in there. Like, just because, yeah, you can do queries and everything, but yeah. Saying it's a relational database is kind of stretching it for me. And then you can see, okay, we have Cassandra, which is doing kind of okay or not so much. Then we have Redis, we have Elasticsearch, and we have some others. So these are kind of the top 15 databases in the world we have. And I just picked a few pretty randomly. So I want to look into MongoDB, since it's the most widely used NoSQL data store. I will look into Redis, Cassandra, Postgres, and Elasticsearch. So let's pick each one of these, and let's just look at one specific use case or thing where I think that they are doing a very good job, or what they might be interesting for. So first off, MongoDB. But let's say it's just like document stores in general. So if you want to use CouchDB, Couchbase, Elasticsearch, whatever stores documents, or let's say JSON, since all the modern ones are storing JSON, pretty much the same applies. And there is this famous quote by Ted Neward, ORM is the Vietnam of computer science, which I think that post is like 10 years old by now. And back then, ORMs were in a worse shape than they are today. But he kind of said, like, yeah, you have this impedance mismatch where you have your nice objects on the one side, and then you have your also nice but different relations on the other side. And there's always kind of this problem of matching the two together. And he had various points, like you either abandon object orientation or you abandon the relational model, or in various degrees, or you kind of find various workarounds. But it's just like these two systems are very hard to make work together very well. And that was what his main blog post is about. So let's just pick one quick example. Who has done something like that? If you have an end-to-end join and you want to be able to navigate that and join that together, who has done that? Is this okay? It works, yeah. It's pretty much that. I'm okay. Some would even call it the Stockholm Syndrome. Like, yeah, you kind of get used to it at some point. It's kind of annotation hell. But you can kind of feel like you have these two systems, and you can just feel it's a bit of a pain to make them work together. So let's take a very simple example. We have an abstract base class person with one attribute, and person is extended by employee, which works for a company. And then employees are split into managers and workers. And you can see managers can approve funds, and workers have experience, while managers don't have any meaningful experience. I hope we don't have too many managers here. And we just want to store that. And if you're using a relational database, you basically have 3 options how you can break that down and store that in your relational database. So the first one would be you have a union table, you have one table, so you have the person would be probably the name of the table. So you have one table to store all of your classes in there. Downside is you potentially have a lot of null values, especially if you have a lot of specific implementations and they have varying attributes. You will have a lot of null values. And that is kind of a pain because often in your relational database you want to have like these nice little attributes like not null and have some constraints of what you can put in there. But if everything is pretty much optional because you have so many different implementations, you cannot really use those. And also your relational database at some point looks more like Swiss cheese than a relational database because you have all these optional attributes. Okay, what else can we do? The other option would be you just make concrete implementations. So in the end, you could have employee, employee, worker, and manager. So all your concrete implementations which you could instantiate get their own table, and you just put in whatever you have there. So you don't have any optional attributes anymore. Everything should be there. The major downside is if you want to get all your employees, you will need to do a union clause to actually combine all of these different tables together to find, for example, all the employees working there or find all the people you have stored. So yes, while you can make that, you can see like on your objects, it's kind of like very simple to see what you have, and you don't really need to kind of join together stuff and put different things together, whereas in the relational model, it just doesn't really fit that well into one schema, and you always need to work around like by joining stuff together. The other alternative would be every class gets its own table, and whenever you need to have something that is deeper down the inheritance level, you just need to join together with all the previous ones. So you have a person table, you have an employee table, you have a worker and a manager table. And if you want to have a manager, you will need to join person, employee, and manager together through all these three tables to combine all these attributes together. Which again feels more like workaround. So how can document stores actually help here? Let's take a very simple example. Unfortunately, with PHP, you will need a lot of annotations for that. So we have our abstract class person. We say it has an ID. I keep my name. It's a mapped superclass. And then you pretty much say, OK, I have one. It's called collection in MongoDB, but think of it pretty much like a table. We have one of these collections called person. And we will throw in all our specific instances in there. And they will get an additional discriminator of the field name type. So they will have a field type. And that will actually tell which concrete instance is it. And we're adding our company name here. And our explicit implementations then are just, you annotate that with document. And then you just say approved funds and years of experience. And that is all you need to put together. And what you get then in your document store, MongoDB in our example, is you just have all of that in one collection. You don't have anything optional, since JSON just leaves out the attributes that you don't need, and you just have the attributes that you have. And if you want to get all the people in your data store, you can just fetch everything from here. If you're just interested in managers, you can just say, OK, the type needs to be manager. So you can very easily get down to all the things you need. I mean, there are no joins in MongoDB, but you don't really need them anymore. You have optional attributes, and you can just combine everything together. Main downside of that approach probably is that you have quite a lot of annotations still in your PHP classes. You would not believe it, but even in Java, you can do that in less lines than PHP. Any idea why we have this weird ID? Like, these are kind of less nice than what we would have in a relational database, where we would have some auto-incrementing or serial or whatever you call it, ID, which would be just 1, 2, 3, 4, 5, etc. Why do we have these weird IDs?
No collisions.
Yeah, it's not about really no collisions. The thing is, since you have the distributed system, who hands out these IDs which are auto-incrementing? Like, you would always need to have one instance which keeps track of these. And in a distributed system where you have can have these partitions, it's kind of hard to generate those. So there is a specific scheme behind that. Like in there is a timestamp, there is the MAC address of the computer where the MongoDB instance is running. There is the process ID. So there are lots of values which are put together, and this guarantees that within that collection, that value is actually unique. And you don't have one instance which needs to generate your IDs. With the downside that you cannot tell your colleagues very easily, well, check out record 5312. You will need to tell them, yeah, check out 524D9, whatever. And that all works very nicely. The main downside is, as soon as you go beyond replication and need to shard your data, you will have a lot of moving parts in MongoDB. As you can see here, you have your data pretty much down here, but then you need a routing component, and you have a config server which knows actually which data is living on which server, and then we have these 3 shards, and each shard is replicated 3 times. So at that point, it gets a bit hairy. So for me, my main use case is always, as long as you can just do replication with MongoDB, it's very nice. But as soon as you then need to add sharding, it gets a bit more painful. Okay, next up, Redis. Key value store, even though it's a bit more than key value store, the name actually comes from remote dictionary server. So in Python, what would be an array is always called a dictionary, and that is where the name comes from. So it's a key value store plus a bit more. So it has some more advanced data structures. And the one use case we want to dive into is, assume you have people who log into your site. And then marketing tells you, well, I want to know who logged into our site over the last hour. And then you can very easily store that in Redis. So you have 2 data structures which you can use. The first one would be bitset, and the other one is called hyperloglog, which has a very fancy name. So bitset is basically every user registers on your site. And that user gets a unique auto-incrementing ID. So you have user 1, 2, 3, 4, etc. And then you assign a bit to each user. And then you can just say, for 1 hour, you just instantiate a bit set all with zeros. And as soon as one user logs in, you flip his bit at that position. So if the 5th user, whoever registered, logs into your site, you flip the 5th bit from 0 to 1. And then you could very easily track like who has logged in. So for 1 million users, you use per hour approximately 123 kilobytes, which sounds pretty manageable, especially after 1 week, for example. You probably don't care about the specific hour when somebody has logged in, but just the day. And you can very easily combine that. So you just take all the 24-hour or 1 hour slots, 24 in 1 day, or connect all of them and get a 1 as soon as somebody has logged in within 1 hour. So you can very easily aggregate that data later on. The other one is hyperloglog, which sounds very fancy, and it is only a probabilistic data structure. With the big advantage, you just need a fixed amount of data. So you use 12 kilobyte, and it can count unique values. Downside is only probabilistic, so it's not guaranteed that that user has logged in. But you have like a 99% guarantee that if you check has user X logged in, you can say yes or no with that data structure. And it doesn't grow anymore after some, or the data structure is fixed with that very limited error rate. So in general, the hyperloglog is nice because it is constant size. Bitsets are nice because you can easily aggregate them. And often the marketing team says like, yeah, 99% certainty is kind of nice, but I want to be sure. Like I want to spam those users who logged into our site yesterday. And I don't want to spam anybody else. Why you shouldn't spam anybody? Yeah, probably only really send emails to those people who actually logged in. So with the bitset, you can aggregate them and they're exact. So bitsets can also be nice for that use case. Generally, I always have the feeling that Redis is kind of this omnipresent glue, like nearly everybody is using Redis, where you can use it as a cache, session store, lots of other things. Who's using Redis? Okay, quite a few. Everybody happy with Redis? Yes? Yeah. Redis is a nice system. It's super simple. It's basically, Salvatore Sanfilippo is basically, he's based in Sicily. He's writing that pretty much on his own with a few contributions. But it is a very nice project, and I think, doing very well. Next up, Cassandra. Cassandra is actually kind of making fun of Oracle, because if you remember Greek mythology, like Cassandra was the one who saw the future, but nobody believed her. And I think then some god sent snakes which killed her, so she couldn't keep telling everybody. Whereas the Oracle of Delphi didn't know anything. They were just sitting in their fumes and hallucinating. And that is kind of making fun of that. So the Oracle guys, they don't really know anything, they're just telling random stuff. Whereas Cassandra really sees the future. That is where the name comes from. And the main, or the nice thing is it's really scalable and it's really highly available. And kind of the idea behind that is consistent hashing. And I think Cassandra is pretty much the only system where you can put in 1,000 nodes and it will still work as expected. Downside is not everybody has a problem of needing 1,000 nodes. So consistent hashing looks something like that. No worries, it's a bit small. We will dive into each one of them quickly. So the first thing is everything has an ID, and you just give it some ID value. And that ID value is hashed. Any ideas why it could be or should be hashed? Sorry? Yeah, for MongoDB, normally you generate that on the client side. Here the thing is you assign the ID yourself, but for example, if you assigned the email address or something, the email address is probably not very evenly distributed over your entire key space. And by hashing, you make sure that the keys are very evenly spaced out over your entire key space if you use a good hash function. Otherwise, you probably have, what is the most common letter in Serbian? E? A? Okay, in German it's E, in English it's E, in Serbian it seems to be A. So normally you would have, depending on the distribution of the letters, if you just use something like a name or an email address, you would have a hotspot around that letter. And to avoid that, you will do that hashing. So if you do the hashing, all your data should be evenly distributed over your entire key space. And you just, in our example, we assume we have 3 nodes, and we will just cut the key space into 3 evenly distributed parts. And then you kind of turn the entire thing clockwise. So you can see this is our key space, we have it clockwise. This is not kind of the physical location. This is not like a token ring network. This is just a logical view of data. So we're hashing our X value, and the hash value lands on node A, as you can see in the first circle here. It's going to node A. And how you get resiliency out of that then is you always replicate it to the next node. So you can see the hash X value is then being replicated to the B node as well. So that kind of dashed line is going to B. So it's stored both on node A and node B. And then we're hashing Y. Y is landing on node B and is replicated to node C as well. And if you want to have more than one replica, you would just go one node further. So you can very easily distribute that over that. And then you can very easily either remove nodes or add nodes. So this is the example we had on the previous slide. If we want to add another node D, we could just take the key space of A, basically, cut that in half, and migrate all the data from the A node, half of the data from the A node to the D node. And you can see it's still on the ring, and something hash X then lands initially on the D node and is replicated to the A node. Or if one node is either explicitly removed or fails, all the data is just like forwarded to on the ring. So B is dead, and everything goes to C now. And it also figures out like, well, there is no replication anymore. I need to replicate the data to A as well. And that will all happen just in the background for you, and you don't need to tune anything. So it's very easy to actually add nodes and remove nodes, and it's kind of all happening magically in the background. And the final step you will normally do is you will have something called virtual nodes. So you will split up your key space into much smaller chunks and just distribute them evenly. So if one node fails, you don't have to replicate all of the data of node B to node C then, But if you have split it up evenly over all the nodes, if one node fails, like every server will get a small fraction of the data of that one failed server. So you will have more of these virtual nodes, even though you still only have, for example, 3 physical nodes in that example. And then the first node would get a piece of each of the areas, basically, and you can evenly distribute that over your entire ring. So if one node fails, you don't have that much network traffic and data moving around. The one thing with that model is that it's not consistent as in the cap theorem anymore. So yeah, some people had to suffer through that. Cassandra always say they're tunably consistent. So if you write your data to 3 nodes, you can always say, I want to at least write my data to 2 nodes and read from 2 nodes. And then I'm sure that I will always get the most up-to-date data. But that has also more overhead than you would need. So it is tunably consistent, but having a consistent view in Cassandra adds overhead. And a lot of people don't want to do that, so they will go for something that is not immediately consistent. One other kind of side note, the consistency in the cap theorem is a different consistency than in ACID. So in ACID, the consistency is pretty much going from one valid state to another valid state, like you have constraints, you have references, you have not null, you have data types. The consistency is there on the data model, whereas the consistency in the cap theorem is kind of a temporal approach or temporal thing. Like at one point in time, you get the same data from all your nodes. That can be very confusing that you have consistency there, but it's an overloaded term, and depending on the context, consistency means different things. And yeah, some people then say, this eventually consistent thing that Cassandra does is too hard, so you can go for immediately inaccurate. And that is much easier to understand. Inaccurate is inaccurate. Okay, kind of the other side is Postgres. Postgres got again very fancy and popular because they have been working on Postgres for like forever. It has a lot of features, it is very stable, it is very mature. It's not owned by Oracle, so lots of people love Postgres. And one common complaint about relational databases is that they're slow. And you can see in that comic somebody says like, oh, my database is so slow, and I have made this battle plan, and I will rewrite everything in some NoSQL system, and I have made already the project plan and the Gantt chart, and we will rewrite that over the next 4 months or something like that. And then the other colleague says, well, let me check. You didn't set the right index. So I set the index, and suddenly everything is 20 times faster. And I think Anna is doing a talk about that later today, where she speeds up your database 300 times by setting the right index. So I will not go deeper into the index level, but there is another talk this afternoon. If you want to know more about relational database indexing, go to that talk. And the other thing is that relational people often say now that relational databases are actually really SQL databases because the SQL standard has moved beyond the relational model by now. So you have JSON in the latest SQL standard, SQL 2016, you have JSON in there. So it's not only about the relational model, it's kind of they start to add more and more features that you would expect from the NoSQL world. And on the other side, the NoSQL world started to add their own SQL-like query languages, which are often more confusing than they're helping. So for example, Cassandra has their own query language, CQL, which looks a bit like SQL in the beginning, but you will actually figure out, A, it is limited, and B, you will always need a secondary index for every column you want to query. So that will add quite some overhead. And then lots of other people followed along. So you have the Google query language, you had RethinkDB, which I'm not sure if that is still around anymore. It's kind of has been given to the community. Let's see how that develops. ReQL. Couchbase was a bit more creative. They called their query language Nickel, but it's still the same thing. So you have whatever query language which is something like SQL because everybody knows SQL and everybody can write that very easily. And it's much easier to get started than learning some new query language. So generally what you get in the relational space is you get the features and maturity of relational databases, and you get the NoSQL influence, basically. So replication is getting better, you get JSON, so it's not always needed to actually use a NoSQL store anymore. And then the final system is Elasticsearch. But that is not really, we never say it is a database, we always say it's a data store, because kind of the sweet spot is basically for full-text search. Who's good with Star Wars? What is the quote here? Yeah, exactly. When he makes this hand movement, these are not the droids you're looking for. So let's quickly see what full-text search actually does. So I've added this HTML tag here for emphasis. These are not the droids you're looking for. And what you do is when you store data, you actually do a full analysis of that. And that is the main difference why you should not do something like I like in a relational database, because A, it's not doing the exact same thing, and B, it will be very slow. So what happens here is the first thing you normally do is you just throw out the HTML, since you don't really care about the formatting. Like nobody is searching for the tag EM, so you just get rid of that. Then you tokenize everything. Tokenizing basically says, in Western languages, extract each word, split up on spaces and punctuation marks. Chinese and Japanese is different, but let's forget those for a moment. So you can see I have these tokens, bit more space between them. The next step is normally you just lowercase everything. Since you don't, if you search for something, you don't really care about upper and lower casing. You just lowercase everything. So yes, upper and lowercase have different ASCII characters or Unicode characters. So we don't care about those here. We just get rid of the upper and lower casing. Then you remove the so-called stop words. Stop words are basically little words that are pretty much in every document, and there's no point in storing them because they appear in every document anyway. So you would just find every document and you're just storing unnecessary stuff. So you pretty much from, these are not the droids you're looking for, you end up droids you looking. These are the non-stop word words which are in that sentence basically. And then you stem them. Stemming basically means you cut off the ending of the word because you don't really care about if somebody searches for droid or droids. You are more interested in the concept. So droids you looking will be stemmed down to droid you look. And these are the tokens which you then store for full-text search. And every time you search for something, the search terms will run through the exact same pipeline. You will extract those tokens, you remove the stop words, you do the stemming, and then you just try to match what you have here. These will be just stored in a very long list, which is alphabetically sorted. You will just try to find these matches there, and that is what full-text search makes it very fast, and what allows you to actually search more for concepts than just exact matches. And then you can actually score that, like there's always this quality attribute, where you don't just care about like you have exactly the same thing, but probably something that is similar. So the scoring thing is kind of its own complex field. But the very quick version of that is you have something like a term frequency. If your search term appears more often in one document than another one, that document is probably more relevant. So if you search for droid, and one document contains droid 5 times, and another document contains droid 1 time, the document containing droid 5 times is probably more relevant. The inverse document frequency basically says if you're searching for multiple terms, and one of them is very common, and one of them is very uncommon. The very uncommon one is much more important. So for example, if you search over the Star Wars films, the text, and you search for droid and father, droid probably appears in many, many places, and it's generally not that relevant. Whereas if you search for father, there are very few places where the term father will actually appear in Star Wars. But that is then much more relevant, both because of the term frequency, inverse document frequency, but also because father is just very important for Star Wars. And then you have the field length norm, which it's very intuitive. If you have a short field and your term appears there, it is very relevant. If you have a very long field and your term appears there, it's less relevant. It's basically, if you search emails and your search term appears in the subject, which is short, this is probably more relevant than if it's appearing in the very long body of the email. And then you can combine all of these factors together, and it will tell you how relevant a document is. So you will always get this score, which is not just a match or a not match, but you will always have this quality aspect of how good is a match. To finish up, databases have kind of a long history. I didn't do that, but I really like that one. This is kind of like how databases developed. So in the beginning, you did not have SQL. And then in the 80s, it was suddenly like, oh, SQL is the cool thing. Everybody needs and should do SQL. And then in 2000, it was, oh, no, this SQL thing is too slow. Nobody wants to do that. And then people said, like, maybe it's not that bad. I just need something in addition. And then, depending on how you see that, the pendulum might kind of swing back, and then people were like, no, this whole NoSQL thing, that was garbage. Like, I just need a relational database. I don't care about the rest that much anymore. And then there's this very common question, but is it fast? Do I have any meaningful benchmarks now? Unfortunately, no, but I will tell you why not. This is one of my favorite comics, and you can see somebody is benchmarking a squid and a house cat. And under similar conditions, the squid is much more intelligent than the house cat. And that is pretty much what every database vendor does when they benchmark themselves against their competitors. And like 2 years ago or something like that, MongoDB, Cassandra, and Couchbase, each one of them did benchmarks against the other two. And each one of them managed to be at least twice as fast as their two competitors. Because everybody found some scenario where they were really good, or they were using a very old version of their competitor, or a very old driver, or a very stupid query, or something like that. So whenever you see some of these benchmarks where somebody is benchmarking their own product against somebody else, I would be very careful if that is really applicable to your scenario and how you try to do stuff. That's why I would stay away from any vendor-provided benchmarks. And even if just somebody is benchmarking their own product or their own project, be careful only if you have kind of the same queries, the same amount of data, the same usage patterns, the exact same versions. Only then it's probably telling you something. Otherwise, it's probably not going to tell you all that much. And this is already a few years old, so you can see there is Redis in there, FlockDB. FlockDB was Twitter's graph data store, which is not really around anymore. But you can actually go through that and see where you end up. So quickly do that. I will ask you in half a minute where everybody ended up. Okay. Who ended up in HBase? One? Okay, very, very few. Who ended up in FlockDB? Who needs graphs? Nobody. Who ended up in Neo4j? Nobody. Okay, no love for graph databases. Riak? Okay, very few. Couch, which is probably Couchbase nowadays. Okay, nearly nobody. MongoDB? Okay, very few. Relational databases. Okay, that is... Well, I don't think like relational databases are not going away. Like at some point people were like, oh, this NoSQL thing will take over the world, and relational databases are a thing of the past. They're going away. I don't think that. Relational databases will be around for a very long time, and they will still be a very helpful tool. But I don't think that NoSQL is really going away either. Like, those projects are maturing, and you can see some use cases are really well covered by some NoSQL solution. So they're not going away either, and you will just find the right mix. And don't make the beginner's mistake like taking on all the data stores, because there is quite an overhead for running that in production. Like, developing everything is fine. I know you're done in 2 weeks, and then you hand it over to the ops team. But the ops team will hate you forever if they need to maintain and backup and restore and monitor 10 different database systems. So be nice to ops and don't use all the data stores. Kind of make a sensible mix. Any questions? I have very few stickers over there, so you need to be quick, unfortunately. And let me quickly take a picture of you. So I can show my colleagues that we've actually been working here. Smile, everybody. Yeah, very nice. Any questions? Anybody? Anybody awake? You picked the bad spot.
Okay, so the trend with Mongo and these NoSQL solutions is that they're getting queries, and the trend with SQL is that they're getting JSON columns. So what do you think about that?
Yeah, so I think, as you can often see, like you're starting at very different points, and then systems start to kind of grow together, and you see what is working well on the other side always, and you start adding those features. For example, MongoDB didn't have anything like aggregations for a long time, and then they added their aggregation framework, where they have these pipelined aggregations, and you can really see, like in the beginning, NoSQL products were very simple, because they were also very new, and they didn't have all the features and all the complexity. And then people started to say, like, yeah, this is nice, but I need this, and I need this. And then they start to add more and more features. And what you also should not forget is that relational databases pretty much also started like that. Like, the relational databases we take for granted today are very different than what they were in the beginning. So it's kind of like growing together. And I still think it makes sense to have different systems depending on the job. But you're probably doing less wrong if you pick a relational database today than if you pick one of the NoSQL data stores and figure out, well, that was the wrong system, or I designed everything the wrong way. I know there is this urge in IT to always use the latest shit, and everybody wants to do that. But yeah, be careful. But I think people kind of learned that, like, everybody wanted to do NoSQL at some point, and then nobody wanted to do NoSQL because you saw lots of failed products. And there is this so-called Gartner hype cycle, like everything is hyping up, and then you fall down because nothing is working, and then you kind of find this plateau of productivity. And I think we're pretty much there with the NoSQL by now. So people know this is good for that use case, but probably not good for that use case. And all the products are adding more and more features. So it's getting more similar, but you can still, depending on your project, pick one over the other, probably. Any more questions? Yeah, two over there. If you don't answer everything, just find me afterwards, and I'm happy to talk more later on. Yeah.
So I have read several articles complaining about Mongo. It's bad, it's terrible, you should never use it. And I'm just wondering why, because I never had really interesting problems with it. Everything is solvable, solvable in a relatively easy way.
I think, so I've used MongoDB in production for 3 or 4 years, and I was always pretty happy with it. But I think, you kind of need to know how MongoDB behaves and works. If you don't know anything and just think, oh, this is super simple, then you will hit the wall at some point. And B, I saw some articles where people were just using it for stuff it was really not meant for. And then it was like bashing MongoDB for that, but it was more like, yeah, you just picked the wrong tool for the wrong job. This is not going to work for you. I think MongoDB is a good product, and with 3.0, they totally rewrote their storage engine. So all the complaints previously, oh, it loses data, and it's like, it's the Snapchat of databases and whatever. That is not that true anymore. I would be very careful with those statements. So MongoDB also improved a lot. They have a very bad reputation because of that. And they had always great marketing and were over-promising, but I think it's a good product now, and it's not there is a reason why it's so high up in the database engine rank. Yeah, final quick question, I think.
Yeah, what do you recommend for Redis high availability? I have used Redis Sentinel, and it's very slow in promoting master to slave when master goes down.
Yeah, so the company who is kind of sponsoring the Redis development is called Redis Labs, and they have their own proprietary implementation for high availability. And I just saw a discussion with Salvatore yesterday where he said, like, yeah, this is kind of the right thing. The thing is, do you really need that replication? Like, depending on your use case, if it's just a cache, like if the cache dies, you just regenerate the cache. And what I find also very interesting about Redis is that they often are kind of shard on the client side. You just say the key space. If the key starts with A to K, go to that server. If it's J to Z, go to that other server. So yeah, you can use it. Depending on where you are, for example, on AWS, they provide it as a service and with replication. If you host it yourself, yeah, if it doesn't really work, maybe it's just the wrong tool or you're using it wrong. Like, I'm always a bit careful. Like, it wasn't really built for that. It's supposed to be a standalone, simpler thing, and yeah, you try to bolt on stuff. If that is really working, I've used only the AWS service that worked well always. But I've never really tried to run that myself. So
yeah, I have tried the Pacemaker, which is much faster, but it's harder to implement and to install and configure.
Yeah, I think like replication was really just an afterthought, so it was kind of bolted on top, and you can see it's not that well integrated into the rest. So depending on how painful it is, it might be the right solution or it might not be the right solution. But unfortunately, that is also a learning experience. Yeah, I think we're having a sponsors talk now, so I'm stepping away. Thanks a lot.